Hey, hello everybody. So I'm happy to present this paper from University of Michigan. And the first author graduated recently, and then he joined, he's at Facebook since the end of April of this year. And then the second author, Gui, he just is finishing up his first year there. And then most of you probably know Kang-Shin from the University of Michigan. Okay. So today I'm going to talk about a paper that's titled as Cross-Platform Support for Rapid Development of Mobile Acoustic Sensing Apps. So nowadays, many phones have some have natural language understanding, right? You can just say to your phone, say something like, hi Sherry or hi Bixby, things like that, and then they understand what you're saying. Or you can also make a course, of course, right? These are the phones. Or you can use your watch to make a course. What that means is that they already have good microphones and then the speakers, such as AKG, speakers that's tuned by AKG, okay? So because of these hardwares are everywhere, right? Microphones and speakers. There are many people who want to leverage this existing hardware on the mobile devices to develop a new, cool, very interesting apps, right? But then, and then this kind of sensing of, especially inaudible sound, can provide like a context-aware sensing, new human, computer interaction, and then almost zero cost, inter-device interactions. But then issue is that, it would be really nice to have this kind of apps for all different kind of devices. However, in reality, it's rarely the case that an app gets, app gets to be developed for so many different platforms. Then why, right? So let's look at the typical workflow of how an app that uses the acoustic signals gets developed. In this app, let's assume that the sensing algorithm itself is the differentiator. Okay, so a developer will develop an Android native app to play an acoustic signal and then record its responses. Then dump the result into a file, and then move the file to a laptop where there is a MATLAB. It doesn't have to be MATLAB. It could be a Python or anything like that. But then, using the MATLAB, which provides so many built-in tools, and then visualization, they do some pre-processing of the signal, and then test the different sensing algorithms to develop new sensing algorithms, right? And then repeat the experiment until they have the perfect algorithms. Then they actually have to copy this whole thing into the native app and then test again, right? And port everything afterwards to another platform. And I just want to point out that these three steps are typically done on the MATLAB, but then it's only available on the desktop version. So that's why there is a burden of going back and forth. And so, what are the problems, right? It's definitely inefficient because you have to dump all those signals and then move the file to the desktop and then test all these things, right? And then it's error prone because the issue is that depending on the hardware, there are so many things that are very specific for different device models, things like that. So, people can make a lot of mistakes, especially when they try to develop it for the new platforms. And then it's definitely not in real time, right? Because when you make a sound and then process it, you want to see the result right away in real time. However, what happens is that in this kind of offline mode, you have to copy the file to the desktop, test it, and then go back to the device itself, mobile device itself, right? And then also the problem is that it's really hard to make your app really independent of an underlying platform. So in order to support cross-platform, what do we need to address? Why are there so many problems, right? So one of the issue is that depending on the device OS, they actually use different program languages, right? Java for Android, Objective-C for iOS. And also the issue is that microphone and then the speakers are very hardware or OS dependent. What that means is that depending on the platform, even they are doing the similar things, they may use the different flags or the configurations, right? For example, let's consider the automatic gain control, which is the thing that prevents you from the signals to be chopped up at the maximum part. So in case of Android, if you turn on the voice recognition flag, it actually automatically turns off to AGC. But then same thing happens with some other flag in case of iOS. The third one, maybe the most kind of painful part is that, tuning the algorithm to the device-specific, hardware specification. The issue is that especially for inaudible range, which is about 20 kilohertz to 22 kilohertz, there wasn't really agreement about how to, what to do with those signals in that kind of hertz, right? Because even from the same smartphone maker, depending on the models, they actually end up doing something different, right? In the previous model, they just tried to ignore it and then chop off. So there was like nothing really hidden in that range. But then later on, they realized that, there could be some meaningful ways of using those kind of ranges, right? And then they actually decided to do different things. So depending on those kind of things, there could be difference on the signal strengths that you can actually play with. So, knowing and tracking all these kind of, differences between the hardware or the models could be very difficult. So we have a solution that addresses these problems. So we want to actually provide, the goal is to provide a cross-platform compatibility and then let developers really focus on the differentiating part, which is the more of the sensing algorithm itself. And then they can just forget about all the rest of the things. So typically what would happen is that they have something, so the authors actually already published the app at the App Store, right? So this is called something LibAS, dev app. So you can search up and then download it on your phone. And what it does is that it's kind of startup package, and then with the library already embedded in there, and then it provides the connectivity to the MATLAB on your server, right? So it actually records the sound and then streams the sounds to the MATLAB, where you can develop your algorithms or visualize it, and then debug your algorithm. Okay, and then so once you are at that initial stage of development, you can actually customize the UI in order to really publish your app to the at the App Store, right? And then in order to optimize it, once your debugging is all done, you can now actually use the MATLAB. MATLAB actually provides something called a MATLAB coder, which automatically converts the MATLAB code to the C code. So by using that, and then once you generate it, it already has the LibAS library integrated into it. And then with your customized UI, you are ready to actually publish it at the App Store. Okay? So let's look at what LibAS, take care of for you, right? It actually does the hardware control, audio buffer control, and then pre-processing and data streaming. So all those things are taken care of by the LibAS. What happens is that from the microphone, you sense the signal and then send it to the remote MATLAB on the server, and then you develop certain filters or the sensing algorithms, and then you can test it and then debug your code. Okay, so this shows entire flow of what typically would happen during the development phase using the remote and then the standalone mode. Okay, so what LibAS does is that it actually supports various platforms, including Android, iOS, Tizen, Linux, and Windows. It provides the communication mechanisms so that the developer doesn't have to worry about that part. And then it's almost a zero overhead, right? Because you can just focus on writing the MATLAB code on the left side, and then using the dev app, you can test your initial code. And once that phase is done, you can convert your mainline code to the C code, which will be the standalone mode, right? And then you can then publish your app at the App Store. And it also provides, additionally, it also provides some extensible programming interface, meaning that it's not just the acoustic, signals that it's going to take care of, but you can also specify, other data that you want to send along the acoustic data, because oftentimes by combining the multiple sensor input, you can boost up the performance. Okay. And so at the end of the talk, I will give you the GitHub repository, and then it's already been open sourced, and then there are demos and examples where you can actually start using and playing with it, okay? So using the LibAS, you can download the dev app from the App Store, and then using that one, you can connect it to the MATLAB on the server side, and you can focus on the designing the sensing algorithms. And then you can check and then debug. And then once that's done, you can download the SDK, which includes the LibAS as a library. And then optionally, you can also convert it to the standalone mode with the C. Right? Because the thing is that at MATLAB, it doesn't really supports the Android, exporting to the Android, for example, but then it doesn't really support for Tizen per se. But then LibAS kind of hides all those, hardware dependency or platform dependencies. So now you can just export it with the LibAS plus the C code, which can be then deployed on the Tizen platform. So you can prototype sensing algorithms easily with the remote mode and then productize them by turning the standalone mode. Okay? So I'm going to go through one of the examples. I think there are 3 examples in the paper, but we're just going to cover one of them here. So there is something called the Sonar example. What it does is that it turns the device into a Sonar-like system using inaudible chirps, and then senses the closest object and then show the result in real time. Okay? So the first thing is that you write a MATLAB code, which is the main function, and then registers the callback function. And one of the things that you have to do is that you have to let the app actually specify the server, right? And then this is the interface that you get from the dev app that's provided at the App Store. Okay, so you can specify the server IP, and then specify which microphones that you will be using and which speaker that you will be using. Okay. And then once that's done, you also need to write the callback function, which is specified if the data actually comes in, what are the actions that you will be doing. So you can just focus on the algorithm themselves when using the LibAS, okay? Okay, so once in the remote mode, you develop, all these things very easily, right? Without writing much of many lines of code. And then once that's done, the next step is to convert the version to the C mode, to the standalone mode, right? So the first thing is that you want to develop the MATLAB callback function, and then using that, you want to generate the C code automatically using the MATLAB's MATLAB coder functionality. Okay, and then it dumps the C and then the header files, and then you can actually incorporate with your app code. Okay, so there have been already real users who are using the LibAS. So the one is the phone manufacturer, and what they did was that it was originally, there is something paper called Force Phone from MobiSys 2006 from the same authors. And then what they did was that using the acoustic, sound, they tried to guess, the pressure that people are using on to enable certain menus on the phone. Mobile phone. And then once that was done, we wanted to actually convert it to the other platform, so they actually used this LibAS to do so. And there was another example from the University of Michigan group, and then what they did what they tried to do was to do the localization project using the acoustic signals. Okay, and instead of writing all the code in Java, they were able to do it in the MATLAB easily, and then convert it later on. Okay. And then also, it wasn't just the people who were involved in this project who worked on it, but then there were some requests from the other universities who actually wanted to use these libraries. Okay, and then many of the codes are already at the GitHub, so you're welcome to take a look. And at the end, what happened was that because originally they had to write it in the native app code, and then using this LibAS, they actually were able to save a lot of coding, and then statistically speaking, they actually were able to save 80 lines of the code in average. Okay. So, and we already have the code at the GitHub, but then we are still working on the documentation, and then the new version will be out very soon. Okay. So that's it. Thank you.